All right, we are on our way to look at section 4.4 trig functions at any angle. So right now we have worked specifically with the unit circle, and now we're going to be looking more in terms of any point, not just a point on the unit circle. Our definitions change slightly. So what's important here is if I pick any point on the coordinate plane, right? Any point, doesn't matter where it is. I can call that point x comma y. So if I, for example, picked this point right here, I picked this point, I could call it x comma y. What that does is it creates an angle theta, and I could still take sine, cosine, tangent with our initial side and the line passing through that point that I picked. And now that point does not need to be on the unit circle. It can be anywhere. So what happens is, similarly to how we worked on the unit circle, I can still create a triangle here drawn in red. That triangle still has certain relationships, but I actually know some of the measurements. Because I know this coordinate, all right, this coordinate means the distance of this bottom side is the distance of x to the right. It means this distance here is a distance of y up, and this distance on the outside, we're going to always call it r. Now, x and y are easy to figure out from the coordinate, but we have a right triangle, which means we could apply the Pythagorean theorem and say x squared plus y squared equals r squared. R being the distance from the origin to our point. So because r is a distance, it will always be positive, and I'm going to say that throughout this video. So two ways to write r. I don't care if you write it like the Pythagorean theorem, or as I wrote it here in your definition. Two ways to find r. They are 100% equal. Okay, so we used to say sine is equal to opposite over hypotenuse. Well, now, when you're given these coordinates, you can look at sine as this side is still opposite here, right, from theta. This y is still opposite. This r is still the hypotenuse. A new definition for sine, y over r. Similarly, cosine used to be adjacent over hypotenuse. Now you can say x over r, meaning the same definitions, just used in a different way. We used to say tangent is opposite over adjacent. Well, now we're going to call it y over x. And then for cosecant, secant, and cotangent, it's all just the reciprocals, similar to how we have learned in the past. So let's take a look and see how one of these problems work out. Let negative 3, 4 be a point on the terminal side of theta. Find the value of sine, cosine, and tangent of theta. All right, so you don't really need a x and y axis here. You know that negative 3, 4 is out here, meaning our initial side is here, terminal side here. This is the angle theta we're looking at. Now I want to know the sine, cosine, and tangent of that value of theta. Well, we know this point, negative 3, 4. What I don't know is I don't know r. So I know this is negative 3, I know this is 4. What I don't know is this point r, and I use my formula to calculate it. R is equal to the square root of x squared plus y squared. If you plug that into a calculator, you're going to get, or you know your 3, 4, 5 triangles, you're going to get r equals 5. Once you have this, it's just plug into the definitions from the last page. We said sine theta is equal to y over r. So that's going to be 4 over 5 cosine theta. Plug in, that's x over r. Negative 3 over 5. And you got tangent theta. Also from the definitions, y over x. That one you actually didn't even need to do this work because all you needed was 4 over negative 3. There's always people who ask, what if I want to write negative 4 over positive 3? Both of these answers are good. So far right there, a pretty straightforward problem. What I'd like to do is take a second. All of your trig functions, depending on what quadrant they are in. All right, quadrant 1, 2, quadrant 3, and quadrant 4. You should know that sine, cosine, and tangent are all positive in quadrant 1. That changes in quadrant 2. So think of x comma y is positive, positive, right? Well, in quadrant 2, it's negative comma positive. If you think, again, r is always positive, so if you think of sine as y over r, sine is going to be positive. That sine is going to be a positive. What you'll have, cosine is going to be an x value, which in quadrant 2, x is always negative. So cosine will be negative. Also, tangent is going to be a y over an x, which is a positive over a negative. So tangent is also going to be negative. In quadrant 3, oops, 1 second there. In quadrant 3, you can think of it as their coordinate is always negative, negative. Which means if you're talking about a sine being a y value over r, which again is always positive, your sine value going to be negative. Cosine works the same exact way, except you're taking your x value. Both of these in quadrant 3, sine is always negative. So if you have a terminal side in quadrant 3, sine and cosine will be negative. Tangent being y divided by x, that's a negative divided by a negative. Negative over negative will be a positive. So a tangent theta that has a terminal side in quadrant 3 will always be positive. And last but not least, if you think of quadrant 4, it's always a positive comma a negative. So you're looking at your sine values. Sine ends up being always negative because it's y over r. Cosine ends up always being positive. And your tangent ends up being, again, y over x. That's going to be a negative over a positive. These are just some ways to familiarize yourself with the trig functions. Okay, so we're going to use that exact chart from the last page right here. So two things. They have given me tangent theta is equal to negative 5 over 4. Now, what I don't know is the 5 negative or is the 4 negative. One of them is, but they've told me cosine is bigger than 0, so cosine must be positive. Cosine theta must be positive. Cosine theta is positive. Well, that actually only happens in 2 quadrants. It only happens in quadrant 1 and quadrant 4. So right off the bat, I know that if I go back one slide, cosine is only positive here and here. So I am either in quadrant 1. I can't be in quadrant 1 because if you recall, overall tangent had to be negative. Because if I go back to, tangent has to be negative. I can't be in quadrant 4. So they've given you this information so you can figure out this has to be in quadrant 4. In quadrant 4, think of your coordinate. Quadrant 4 is always a positive comma a negative, which tells you tangent being y over x, tangent has to be y equal to negative 5, x has to be equal to 4. We can solve for r using the same math we've used before. 4 squared plus negative 5 squared, and then we take the square root. That is going to be r, so that's 16 plus 25. That looks to be like r is the square root of 41. They want us to find sine theta. To figure out sine theta, I know my definition is y over r. So my y value, negative 5. My r value, square root of 41. Negative 5 over the square root of 41. Of course, that's not properly simplified. So negative 5 radical 41 over 41 would be the correct answer. Secant theta similarly has the definition r over x. For this one, my r value, same radical 41. My x value is 4. So it becomes radical 41 over 4. All right. Here we're going to look at reference angles, and this is kind of a tricky definition. So if theta is any angle anywhere in the coordinate plane, all right, any degree measure, 0 through 360, 0 through 2 pi, all right, then the reference angle, noted as theta prime, is the angle formed by the terminal side. So like if I was to draw an angle out into quadrant 2, normally I would call this theta. All right, but what my reference angle is, my theta prime is the terminal, it's always acute, all right? It's the terminal side and the x-axis, but it has to be acute. So you're never going to be, so reference angles are always between 0 and 90, all right? Obviously, in quadrant 1, the reference angle wouldn't change. But in quadrant 2, you can see my reference angle would be this green angle right here. In quadrant 3 and 4, it looks a little different. Let me show you. In quadrant 3, if I was to draw theta, regular old theta, out into quadrant 3, then theta prime is the acute angle right here outlined in blue. Same terminal side, but it has an initial side of the x-axis. If I did this in quadrant 4, my reference angle looks very... so my theta in quadrant 4, if I drew an angle anywhere in the quadrant 4, that would be considered theta. Theta prime would be the acute angle right here, formed between the terminal side and the x-axis. So it's just a way to simplify our angles from something large to something between 0 and 90. When you do that, your signs get a little trick there. You have to pay attention to your signs. Okay, so I know 300 degrees is into quadrant 4, right? If I drew 300 degrees, it would look something like this. The question is, my reference angle is this very small portion right here. How big is that part? That's going to have to be, has to be 60 degrees. So theta prime, reference angle, 60 degrees. Notice this next measure is in radians. So because you know pi is 180 degrees, you should be able to figure out this is in quadrant 2. 2.3 radians is, and this is approximating, this is approximately 2.3 radians. Well, the question is, how do I get my reference angle? Well, I know my whole angle. I know this is total, that's pi. And I don't want this blue angle that I already drew in here. So I'm going to use subtraction. To get theta prime, I'm going to do pi minus 2.3. Negative 135, if I was to draw this. Negative 135 would come out into quadrant 4. That would be negative 135 degrees. Again, my reference angle falls between the x-axis and my terminal side, so I need theta prime, my reference angle. Well, I know the whole thing's 180, so it leaves this part, this whole half is 180, so this part has to be 45 degrees. My reference angle, 45 degrees. Okay, here, this is just a little practice using the unit circle. I think all of these you'll find on the unit circle. You might have to use a reference angle, but here's a little review because we're still using that unit circle. Here's a little practice. Be careful of your signs while doing that, but I'm assuming you can do that on your own. Let theta be an angle in quadrant 2 such that sine is equal to 1/3, and find cosine. All right, so what have they given us? They have given us, going back to our definitions from the very first page, sine is y over r. So they've given us y is 1, r is 3. They've also told us to be looking for cosine. So remembering that always critical relationship, r equals x squared plus y squared, from the very first slide of today, we actually know r and y, which means we can do 3 is equal to square root of x squared plus 1 squared, and I have enough information to solve for x. To do that, I'm going to square both sides, because squaring both sides will cancel out the radical, and I'll have 9 equals x squared plus 1. From here, it's minus 1. X squared equals 8, and I square root both sides. X equals radical 8. Of course, I don't really like radical 8 because it can be reduced to radical 4 times radical 2, and better known as 2 radical 2. So now I have this value. I know x, y, and r. And in fact, I could give you, now the tricky part to this problem is you are in quadrant 2. In quadrant 2, what do you know about all of your x values? I know that y is always positive in quadrant 2, but all my x values are always negative. So because I have determined that this problem is in quadrant 2, I have to remember to put a negative sign in front of x to make this problem work. So when I go to answer here, cosine theta, the common mistake is to write 2 radical 2 over 3, but this is actually an incorrect answer because you need that negative sign. This negative right here is probably the most common mistake on any quiz or test that you're going to take this chapter. paying attention to what quadrant you're in and the sign of cosine